Hi, my name is Se-eun, and I'm here to present our paper, How Much and When Do We Need Higher Order Information in Hypergraphs, a case study on Hyperedge prediction. What are hypergraphs? This is the kind of graph that we are familiar with. It captures the interactions of two entities with edges or links. But around us, we can see interactions of more than two entities. For example, when we write a paper, we usually collaborate in groups. And to represent such group interactions, we need hypergraphs. It captures the interactions of arbitrary numbers of entities with hyperedges. Uh, a problem with hypergraphs is that they're not straightforward to use. So, a common practice is to simplify them, for example, into ordinary graphs. And perhaps the most widely known method is the projected graph. You can see the hypergraph here, and we can turn them into a projected graph like this. For example, the edge weight between node 3 and 4 is 2 because 3 and 4 have appeared twice in the original hypergraph. So a projected graph captures two-way information in the original hypergraph, and obviously we cannot recover the original hypergraph from the projected graph, and this means information loss. So many studies propose methods to use the whole hypergraph so that we don't have information loss. For example, the incidence matrix and sequences of sets and the hypergraph neural networks. So we can see that previous studies either used two-way information or they used all the information. And there is accuracy complexity trade-off. Our question is what happens in between? For example, we can use three information, four information, and the more we use higher order information, we will get more accuracy with the cost of complexity. And if we can know how much accuracy do we gain by using more higher order information, this may be a useful engineering guideline to hypergraph tasks. So we would like to know how much n-way information do we need for accurately solving a hypergraph task. And to answer this question, we need to devise a method to capture n-way information. And in our case, it is the proposed n-projected graph. We choose the Hyperedge prediction as our task, and we measure prediction accuracy as n grows. To give you an illustration of all this, this is Hyperedge prediction. For example, we want to predict whether 1, 2, 3, 4 would collaborate in the future. And knowing how often pairs have collaborated would be useful in solving this task. But if we additionally know how often three people have collaborated, this would be even more useful. This is because, for instance, 1, 2, 3 have collaborated before, and 1 introduces 4 into the group. And as a result, 1, 2, 3, 4 writes a paper as a group of 4. We formulate the Hyperedge prediction as a binary classification problem. First, we remove some hyperedges in the original hypergraph, like this, and this becomes the set of positive hyperedges. We also generate negative hyperedges that didn't exist in the original hypergraph, and altogether this forms the candidate hyperedge set. We can create the candidate set in many different ways, and depending on how we create it, the task difficulty may change. We can control the quality of negative hyperedges, and the better the quality, the more difficult the task becomes. We generate we sample the nodes from the projected graph so that the nodes form either a star or a click. And clicks are more tightly bonded and they become more difficult to distinguish from the actual hyperedge. We can also control the quantity of negative hyperedges, and the more we generate it, there are fewer true hyperedges, so it's more difficult to pick them from the whole Kansas set. Now we move on to the definition of the n-projected graph. This is our way to capture n-way information, and it's based on the idea to extend the projected graph, which is the pairwise projected graph or two projected graph in our case. So this is the hypergraph, and two projected graph is defined like this. Edge weight between 1 and 2 is 2 because 1 and 2 appear twice in the original hypergraph. And likewise, 3 projected graph is defined like this. Edge weight between node 1, 2 and node 1, 3 is 1 because the union 1, 2, and 3 appeared once in the original hypergraph, so the edge weight is 1. And node 1, 4 and 2, 4, the edge weight is 2 because the union 1, 2, 4 appeared twice in the original hypergraph. And the 4 projected graph, edge weight between 1, 2, 3 and 1, 2, 4 is 1 because 1, 2, 3, 4 appeared once, and so on. We can define n projected graph like this. Now, based on the n projected graph, we will define the n order expansion on a representation of the original hypergraph. Now, we use projected graph accumulation. So this is 2 order expansion, this is 3 order expansion, and this is 4 order expansion. So we use up to n projected graphs. And as we increase n, the representation becomes more accurate. Now we have the n order expansion. We can generate a feature vector from the n order expansion. These are the features that we used, and we input the feature vector into a binary classifier and then do a prediction. In our experiments, we use 15 datasets from 8 domains, and we use the AUC-PR as our performance metric. We deliver 3 messages as a result. The first message is that more higher order information leads to better prediction quality but with diminishing returns. If we compare the performance between 3-order expansion and 2-order expansion, we can see that 3-order expansion performs better. The same goes for many different settings. Now the diminishing returns. We increase n up to 9 and see how the performance changes. Although there's an increase in performance, the gain itself decreases. So, which means that small n is sufficient for good enough accuracy. We can observe the similar trends in different data sets. The second message is that if the task becomes more difficult, then higher order information becomes even more valuable. We show this as a heat map. The numbers represent percentage increase in performance, and as the task gets harder, the gain becomes higher. Same goes for other settings. And finally, we ask, why is it that in some data sets, higher order information is more important because the performance gain was different across data sets? We had 2 speculations. First is that those data sets have more higher order information. And to validate this, we captured the abundance of 3-way information as the edge density of 3 projected graph, defined like this. And indeed, we can see a positive correlation between edge density and 2 to 3 order gain. Now the second speculation for those data sets is that higher order information share less information with pairwise ones. So we need to measure shared information between 2-way and 3-way information. We use an information theoretic measure, which is the mutual information and conditional entropy. Now, as expected, we observe negative correlation between 2 to 3 gain and mutual information, and positive correlation between the gain and conditional entropy, which implies that if higher order information has exclusive information compared to pairwise ones, then higher order information is more useful. We asked so far how much, when, and why do we need higher order information, and we hope that our results could be useful for future works on hypergraphs, for example, node classification and node embedding. Thank you very much.